All right, here we go with the Chapter 2 Homework A review, the first of our two Chapter 2 assignments, the one that got extended until Wednesday night. So as usual for these, I go through the results in Blackboard, try to identify the questions that were most difficult, that we had the most trouble with, and then I will cover some of those in this review. The scores overall were pretty good, so we had basically the same average as last assignment. About 10.75 out of 12 was the average score for this week's homework. And that is significantly higher than last year when I taught this course. So we do continue to perform pretty well from a score standpoint. The average number of attempts was still about 3 per student, so that's something I would of course like to see increase closer to 4, get all of you guys to do all 4 attempts, but we're doing reasonably well in terms of number of attempts as well as the average score. Now in terms of the problems that I want to cover today, as you'll see, just about all of these deal with calculations involving primarily photons, frequency, wavelength, energy, the Bohr model, understanding the change in energy as an electron moves between 2 energy levels and how that relates to the photon being absorbed or emitted and so on. And so those are going to be the primarily ones we go over. A lot of those questions had success rates that were pretty low, all below 50%, some even way lower than that. And then a couple of things related to quantum numbers. It did seem like there were a few questions on this assignment dealing with electron configurations, the most recent topic we covered, and those seemed to go pretty well. So I'm not actually going to cover any of those this week, but there might be some stuff related to that on the next homework review that I'll do on Monday. All right, so one of the questions we had trouble with was this one here. We gave and this was the type of problem where you had to calculate the number, the input that we gave you, the frequency was variable. So here we have, so you could have had different numbers in this, but the way you do the problem is still the same. An infrared photon has a frequency of 2,504 gigahertz. What is this wavelength in centimeters? Recall that 1 gigahertz is 1 times 10 to the 9th hertz. That should be superscripted. I miscopied that. But that's sort of the conversion factor that we gave you, which you should probably know anyway, but it was here provided for you. Then we wanted to enter your answer in exponential format with 3 significant figures and no units. Make sure you follow very closely what Blackboard asks you to do, capital E, 3 significant figures, just to make sure there's no issues with getting a question marked wrong for a silly reason like that. I suspect the difficulty with this problem was just unit conversion. So we have the frequency of a photon, we want to find its wavelength. So remember that there's a very simple relationship. Lambda times frequency times lambda is the way I wrote it. Frequency times wavelength equals speed of light c. So if we're looking for wavelength, it's just going to be c divided by the frequency. The issue here is we have to make sure we're using the right units. So we need to make sure that the frequency is in hertz. Here it's given to us in gigahertz. So we need frequency in hertz and we need lambda in meters, okay? And here we're actually trying to find lambda in centimeters. So when we use this equation, lambda equals c over nu, c over frequency, we're going to make sure we use frequency in hertz. That's going to give us a wavelength in meters, and then we have to convert it to centimeters afterwards. So the frequency in hertz is going to be 2,504 gigahertz. And then it's going to be 10 to the 9th hertz in 1 gigahertz. All right, so we're going to use this conversion to make sure that frequency is in the right unit. So that gives us 2.504 times 10 to the 12th hertz. Then we're going to plug that into this equation. So the wavelength, again, in meters is going to be c, which is 3 times 10 to the 8th meters per second, speed of light, divided by frequency in hertz, 2.504 times 10 to the 12th. And that's going to give us a wavelength in meters, which is 0.0001198 meters. And then the wavelength in centimeters, we have to do one more conversion because we're asking for it in centimeters. It's going to be that number. And it's going to be 100 centimeters in 1 meter. So again, we have to make sure we know the conversion factors for the metric units, especially centimeters to meters is 100 to 1. And so we multiply that, we get 0.01 11. And then if we round that and convert it to scientific notation, we would write this as, in Blackboard, 1.20 e minus 2. So this would be the correct way to write it in Blackboard. No units and the correct scientific notation. All right, but the main important thing is to make sure you know how to do the problem correctly. Obviously, following the Blackboard instructions is important too. All right, so that's how we did that one. That's just conversion between wavelength and frequency. The next one deals with a very similar concept. It's just the relationships between energy, wavelength, and frequency. But then we're gonna, in this case, have to use a slightly different equation. So this is dealing to some extent with photoelectric effect, although the concept of the photoelectric effect is not super important in this question. But the minimum energy needed to eject an electron from a sodium atom is 4.41 times 10 to the minus 19 joules. So that's how much photon energy you need for the photoelectric effect to be observed in sodium. What is the maximum wavelength of light? Again, careful with units, nanometers, that will show a photoelectric effect with sodium. So what we have to recall is that we're told that the minimum photon energy is equal to 4.41 times 10 to the minus 19 joules. And the relationship between that and wavelength, we're trying to find a wavelength, it's going to be hc over lambda. So this is, again, one of those other photon equations we should know. And basically what we need is that we want the photon energy to be greater than or equal to that. Now, regardless of whether you write it in this way or write it as an equality, the point is that the energy of the photon and the wavelength are inversely related. So if this is the minimum photon energy, the lambda that we would calculate from this is going to be representing the maximum wavelength. Basically, this is the longest wavelength that would correspond to this photon energy. Any other wavelength that's longer will give a photon energy that's too small. Any other wavelengths that's smaller will give a photon energy that's large enough to observe the photoelectric effect. So all we're going to do in this relationship is solve for lambda. So lambda has to be less than or equal to hc divided by the energy of the photon, which is going to be I think I wrote that the wrong way, so I already screwed myself up. Let's just write it as equality, so not screw ourselves up more. All right, but anyway, we're going to solve for this wavelength is really what we're doing. So h is 6.626 times 10 to the minus 34. C is 3 times 10 to the 8th meters per second. And then the energy of the photon, we're told, is 4.41 times 10 to the minus 19 joules. So when we multiply that out, we get, hang on a second. I left out a digit, 41. So I got 4.51 times 10 to the minus 7, and that's going to be in meters because we're using the speed of light c. So that's meters. And then we want this in nanometers, so we're going to multiply 10 to the 9th nanometers per meter, giving us an answer of 451 nanometers. All right, so the correct answer is C. That wavelength is going to represent the maximum wavelength at which we would observe photoelectric effect. Any wavelength smaller than that would give us photoelectric effect. Any wavelength bigger than that would not. All right, so the next, I think, 3 problems I'm going to go into are actually all very similar to each other. They deal with basically the Bohr model, electrons moving between energy levels in a hydrogen atom, and we're just asking you different things here. So it's going to be really a very similar setup for all 3 of these problems. We're just going to make sure that we know how to get to the answer we're looking for. So in the first one here, which is probably the most straightforward one, we want to know what is the energy in joules of a photon that will cause excitation of a hydrogen atom from the state where n equals 2 to the state where n equals 6. Once you have the value, determine its log, base 10, and then enter your answer with 3 decimal places. So I suspect that last part of the question, the determining the log, may have thrown some people off. But first, let's just handle the chemistry part. So we're clearly dealing with the Bohr model here. We have a hydrogen atom, two different n values. So we should immediately zone in on this equation, which is the change in energy for a hydrogen atom as we go between two energy levels. So it's going to be minus 2.18 times 10 to the minus 18 joules. And then 1 over nf squared minus 1 over ni squared, where nf is going to be the final value of n that we go to, ni is the value of n that we're starting with. So when we plug in the numbers from this one, here we're going from n equals 2 to n equals 6, so nf is going to be 6, and n initial is going to be 2. For this problem, if you switch these two, you're not going to get the answer wrong at the end, but it is good to keep things straight. So for calculating delta U, we need to make sure we put the final value of n first in the equation, initial value second. Here it's going to be 6 and 2 in that order. And so when we calculate this out, what we get is a delta E. Let me make sure I did this right. Of 4.84, so that's a 4, 4.84 times 10 to the minus 19 joules. All right, that's the change in energy for the electron as it goes between those energy levels. And remember, when an electron jumps between energy levels, that's going to be either by absorption of a photon, in this case we're going from lower end to higher end, or emission if we're going the opposite direction. And the energy of the photon is just going to be equal to the absolute value of that delta E. So it's just going to be this number, 4.84 times 10 to the minus 19 joules. Now we're told in this problem to take the log. I don't think we have any test questions like this anymore. This is sort of an archaic feature of Blackboard, where it used to be very difficult to do scientific notation in Blackboard, so we just had you take the log of your answer instead of reporting it in scientific notation. So like I said, probably not anything on the test like this, but we should know how to do it for the homework. We have to take the log of this answer, and that's what we report. So the log of 4.84 times 10 to the minus 19 is what we're going to put into Blackboard. And so make sure you know on your calculator how to do logs, because that could come up from time to time. And what we get is minus 18. We went 3 decimal places, I believe, so we're going to be minus 18.315. So that's what we put into Blackboard. I mean, the real answer is this one here. That's the energy of the photon, but then the log of that answer, what we put in Blackboard, is there. So that's one question, just asking about the energy of the photon. Now the other thing we can ask about is either the frequency or wavelength of the photon. So this is the exact same problem, except this time we want to know the frequency in hertz of a photon that will cause the same excitation. Now these numbers were variable inputs. You might not have gotten 2 and 6, but here I kept them the same. So in this problem we would do the same first 2 steps. We would use the delta E equation, and then the energy of the photon being the absolute value of that. But for this one we have one additional step. So if the energy of the photon is what we determined in the last problem, 4.84 times 10 to the minus 19 joules, remember that this photon energy is related to frequency and wavelength. The energy of the photon is equal to h times the frequency, or h times c divided by the wavelength. So both of these equations relate to the energy of the photon. In this case, we're going to use this one because we're searching for the frequency in hertz. So nu is going to be the energy of the photon divided by h, which is 4.84 times 10 to the minus 19 joules, divided by h, which is 6.626 times 10 to the minus 34 joules seconds. And so we're going to get a number which represents the frequency of the photon in hertz. So it's going to be 7.30 times 10 to the 14. And then again, we're going to do the same thing in this problem, determine the log. So this is the frequency in hertz, the log of this answer, which is what Blackboard wanted in this case. Again, no particular reason for taking the log other than that's just a more convenient answer form for Blackboard, especially back in the day when Blackboard was still in an older version. So we take the log of that number, we get 14.864, and that's going to be the answer we would put in. All right, so same setup as the last problem, just one additional step now to find the frequency of the photon. And then one more question that's related, but has a little bit of a twist to it. So we want to know, what is the wavelength in nanometers of the photon emitted when an electron in a hydrogen atom drops from a 3p orbital to a 1s orbital in a hydrogen atom? Sorry for the poor wording of the question. We have in a hydrogen atom twice. But the key thing here is we're trying to figure out the energy, in this case, or sorry, in this case, the wavelength of the photon when an electron goes from a 3p to a 1s orbital in hydrogen. Now I suspect, although it's hard for me to know for certain, that the use of 3p and 1s caused some confusion. But if you'll recall, the Bohr equation, delta E, the one we've been using in the last two problems, one over n f squared minus 1 over ni squared, only depends on n. It's the only quantum number it depends on. So for hydrogen, the energy of the electron is only determined by the first quantum number, the principal quantum number n. So for a 3p orbital, n equals 3 and L equals 1, L being the quantum number that represents p, the angular momentum quantum number. For a 1s orbital, n equals 1, L equals 0. But for this problem, because we're dealing with hydrogen, which only has one electron, we can use the Bohr equation, and we only need the values of n. So we only need to know that this electron is going from n equals 3 to n equals 1. It doesn't matter that it's a 3p and a 1s. If it was a 3s, a 3p, or a 3d, we do the problem the same way. We just need the value of n for this equation. So we're going to find delta E just using the values of n. Where nf is going from 3 to 1, so the final value is going to be 1. This time it's emission, so it's going from a higher value to a lower value, and then 3 is the initial value. So when we calculate this, we're going to get a delta E that's negative because we're going from higher n to lower n. And so what we get is negative 1.94 times 10 to the minus 18 joules. So that's the delta E for the electron. The energy of the photon, which in this case is emitted, is again given by the absolute value of that delta E. So it's going to be just 1.94 times 10 to the minus 18 joules. And then as before, the energy of the photon can be related to frequency or wavelength. In this case, the wavelength is what we want. We're looking for the wavelength, and that's going to be given by hc over lambda. So the lambda is going to be the energy of the photon divided by, hc divided by the energy of the photon. Algebra is hard sometimes. And so we get 6.626 times 10 to the minus 34 joule seconds. We get 3 times 10 to the 8th meters per second. Those are those two constants that we're using all the time in this section. And they're on your periodic tables. You don't have to memorize them, but you probably will if you do enough practice problems. And then the energy of the photon we just found out was 1.94 times 10 to the minus 18 joules. And so when we multiply this out and divide, we get, hang on one second, 1.03 times 10 to the minus 7 meters. We want this in nanometers, so we're going to multiply that by 10 to the 9th again to get to nanometers. And so what we get is, it didn't specify in this problem, I don't think, what the answer format would be, but you would probably enter something like 102.6 nanometers. If Blackboard doesn't specify how many significant figures to use, it's still probably best to use at least 3 in most cases, because that's, make sure your answer is precise enough, but this should be fine whether you put it in as 102, 103, or 102.6. You should get that kind of right. All right, so very similar problem to the last one. The only wrinkle is that we told you 3p and 1s, but the p and the s don't matter for hydrogen in terms of determining the energy of the electron. All right, the next few questions deal with quantum numbers. I think that's what we're going to close out with today, is a few questions on quantum numbers. And mainly the ones we have trouble with are ones that deal with sort of, relationships between quantum numbers, subshells, number of orbitals, things of that sort. So the first one is, how many subshells are there in the 8th shell? So remember that a subshell is going to be defined by two quantum numbers, n and L together. And basically what we have to do for this is, if we're going to find how many subshells are in the 8th shell tells us that n equals 8, we have to know how many different values of L are there. So if n equals 8, each value of L that's allowed is going to define a different subshell. So if n equals 8, the allowed values of L, remember, are going to go from 0 to n minus 1, which means for n equals 8, we're going to have 0, 1, 2, 3, 4, 5, 6, 7. That's going to be 1, 2, 3, 4, 5, 6, 7, 8 different subshells with 8 different L values. So that's sort of the way to do it. That's where this number comes from. So that would be the answer. You would just enter 8. The other thing is, it's not, in this case, a fairly useful shortcut, but it is a bit of a shortcut, which is that, so if you have a shell with principal quantum number, I never remember if I spelled it principal or principal, so I don't know which one's right. But principal quantum number n, there are n subshells. All right? So n equals 1 has 1 subshell, n equals 2 has 2 subshells, n equals 3 has 3, and so on. So this is not a difficult relationship, and it comes from, again, how many allowed values of L there are. So that was one that we had a little bit of trouble with for some reason, but it's a very simple relationship that hopefully you'll remember now. This next one was one that I believe tripped us up for a reason that I'll get into. So we want to know how many electrons can be described by the quantum numbers n equals 3, L equals 3, m sub L equals minus 1. And I think we did an example in class similar to this, but when you're given a problem like this, so the first thing you want to do, make sure the quantum numbers are valid, okay? Because if they're not a valid set of quantum numbers, then there's not going to be any electrons that are described by those. All right, so if we do that here, if n equals 3, which we're told, the allowed values of L, as we talked about in the last problem, are 0, 1, and 2. So if n equals 3, L cannot be 3. This is an invalid quantum number. So that means there are 0 electrons that are described by that. So the first thing you always want to do is check that the quantum numbers we give you are an allowed set. If they're not an allowed set of quantum numbers, if the relationships between n, L, and m sub L are not valid, so remember, n has to be a positive integer, 1, 2, 3, 4, and so on. It can be any of those numbers. But depending on what n is, L is going to be, as we said, 0 to n minus 1, and then m sub L is going to be negative L to positive L. So these are the sort of relationships between them. And if you look at this one, the value of L that we gave you can't be correct because n equals 3, L cannot also be 3. So this one is 0. Now, if the quantum numbers are valid, they're not here, so that's why 0 is the correct answer. But if the quantum numbers are valid, that's where we have to start using some relationships. So if you're given n only, in other words, how many electrons are in a shell, the number of electrons is going to be 2n squared. If you're given n and or L, so if you're given n and L together or just L to define a subshell, the number of electrons is 2 times 2L plus 1. That's the maximum number of electrons in that subshell. Then if you're given all three, as we were here, but they weren't valid, so they didn't really have to go through the analysis, but if you're given n, L, and n sub L together, defining a single orbital, remember that we said because of Pauli exclusion principle, there's going to be a maximum of 2 electrons in a single orbital. So if n, L, and n sub L are all given to you, that defines a single orbital. And as we talked about with electron configurations, you can put at most 2 electrons into one orbital. So this is the relationship we would have used here if the quantum numbers were given were correct, but they're not. So then the correct answer is 0. No electrons can have these quantum numbers because L is an invalid value. All right. All right, this question here, with increasing value of the quantum number L, subshells are named S, P, D, F, G, H, I, etc. It turns out this first sentence was completely useless. So we do give you sometimes extra information. This sentence you don't really need to know. It's true, not wrong, but it's not something you need to know for this one. How many L equals 6 orbitals are allowed in an L equals 6 subshell? So this is just another relationship between the quantum numbers. So up here we talked about the number of electrons that are maximum in a shell, subshell, or orbital. The number of orbitals would just be half this. So in a given shell, there's going to be n squared orbitals, in a given subshell, 2L plus 1 orbitals. So if we have L equals 6, the number of orbitals in that subshell is just given as 2L plus 1. So L equals 6 is not a angular momentum quantum number that we'll see on atoms in the periodic table, but it's one that's certainly possible. And in that case, if L would be 6, the number of orbitals is given as 2L plus 1, which in this case would be 2 times 6 plus 1, which is 13. Now again, where that number comes from, each orbital is defined by NL and M sub L. So you're looking at, for L equals 6, how many M sub L values are there, which again, M sub L goes from negative L to plus L, which would be minus 6, minus 5, minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, 5, 6. So there's 13 different values of L, each corresponding to an orbital in that subshell. But if you just remember the 2L plus 1 relationship for number of orbitals in a subshell, that would give you then this answer much quicker. All right, so that takes me to the end of what I wanted to cover. As I said, overall we did very well on this. But if you have any additional questions, now is the time to get them answered, because we do have the first exam coming up in about a week and a half. So I will be back with another homework review on Monday after the second chapter 2 assignment is due, and I will also see you in class that afternoon.